Hi everyone, my name is Alexandra Lefort and I'm going to talk about the search for life on Mars. More precisely, I'm going to explain what we know, how we know it, and what are our next steps. So, when we talk about life on Mars, what do we mean? Well, pretty much this. We're talking about primitive forms of life, microorganisms such as microbes and bacteria. And we're also talking about life as we know it, meaning life that relies on a similar type of biochemistry as terrestrial life, which is carbon-based life. And we know that life that exists on Earth needs one major component, which is water. So to find life on Mars, we first need to find water. So this is the surface of Mars today. It is a very, very cold desert with daily mean temperatures at the equator of minus 75 Fahrenheit and minus 185 Fahrenheit at the pole. Mars has a very thin atmosphere. The atmospheric pressure is only less than 1% of the Earth's atmospheric pressure. And because of this very low atmospheric pressure, liquid water cannot be stable at the surface of Mars. So any water that we find today at or near the surface of Mars is in the form of ice, particularly in the polar caps, or in vast underground reservoirs, or it's in the form of gas. There is very little water in the form of gas in the atmosphere, only 0.2%. However, if we look at the landforms at the surface of Mars, we notice landforms that are very similar to landforms on Earth that have been carved by water. So the surface of Mars does show evidence of erosion by what looks like liquid water in the past. So this is an image of a valley network at the surface of Mars and one of many valley networks that we have observed on Mars. It is very similar to drainage networks that we observe from space at the surface of Earth. For example, here we have an example of a drainage network in South Yemen. Because of the similarities in morphologies and many additional studies, those valley networks have been interpreted as ancient river network that likely formed by precipitation and by surface runoff, just like valley network formed on Earth, at a time when Mars was much warmer and wetter than today. So we have found many of those networks. Here on this topographic map of Mars, all those red dots represent the different areas where we have found valley networks, and they are located at the border between the highlands, which are mostly yellow here in the southern part of Mars, and the lowlands here in blue in the northern hemisphere of Mars, which suggests that many of those rivers used to flow from the highland into either lakes or maybe even a northern ocean in the northern hemisphere of Mars. Based on those observations and many other observations and measurements, Mars climate models suggest that Mars over 3.7 billion years ago had a much thicker atmosphere and a warmer and wetter climate than today. It may have looked just like this when rivers were flowing into numerous lakes that filled craters and maybe into vast northern lake or a vast northern ocean. And such an environment may have provided the conditions that were necessary for life to appear. What's also interesting to note is that the oldest evidence for life that we found on Earth is dated to 3.8 billion years old. So life on Mars, if it has emerged, may have appeared pretty much at the same time as life appeared on Earth. However, we also have to take other things into consideration when we search for life on Mars, because life requires more than just water to appear and evolve. One of those considerations is that life requires time to appear and to evolve, so the favorable environments are those where the water and the wet conditions have existed and have been stable for long periods of time. Some wet environments are also more favorable to life than others. In particular, environments where the water is at a neutral pH are more supportive of life than environments with acidic waters. Life also requires nutrients such as carbon, nitrogen, hydrogen, and others, as well as energy sources. On Mars, this energy source may be solar energy, chemical energy, or potentially geothermal energy. And some environments are also more favorable to preservations of organism remains, so we have more chances to actually find them. Those environments are in particular sedimentary layers and places that have clays. So based on all of those considerations, the environments of particular interest in the search for life on Mars are ancient lakes, delta, alluvial plains, as well as hydrothermal environments. And those are precisely some of the environments that the Martian rovers have been exploring. So I'm now going to talk about some of the findings made by the rovers Spirit, Opportunity, and Curiosity. The Opportunity rover, which was active on Mars from 2004 to 2018, landed in Meridiani Planum, and this is the type of environment that it explored. One of its main discoveries was the presence of aluminium-rich clays in fine-grained layer rocks, particularly in this area, which was eventually called Whitewater Lake. The presence of aluminium-rich clays is significant because those clays form in water which has a slightly acidic to neutral pH, and on Earth this type of environment is favorable to microbial life. Here we have an image that represents another type of water-related structure. Those run structures were nicknamed blueberries, and they are actually hematite concretions. Those iron-rich concretions form in rocks that are saturated with water when the iron precipitates out of the rock. And they are also indicative of an environment where water has existed for a relatively long period of time. So based on those observations and many more analysis, this area was interpreted as being a very old habitable environment where the conditions were favorable to prebiotic chemistry and to the appearance and evolution of microorganisms. While Opportunity was exploring Meridiani Planum, the Spirit rover was in Gusev crater, an area interpreted as a dried-up lake bed. Among Spirit findings were rocks that were richer in magnesium and iron carbonates than any other rocks studied on Mars. Like the clays that were found in Meridiani Planum, this type of rock formed in a wet environment with near neutral pH water, so an environment that on Earth is favorable to life. Spirit also found Brighton soil, that's pictured here, with 90% pure silica. On Earth, this type of silica forms in hydrothermal environments such as hot springs and steam vents, possibly similar to the similar environment, but possibly similar to the Yellowstone hydrothermal system may have existed on Mars. This type of environment provides heat, water, and the nutrients necessary for life, and is therefore of particular interest in our search for life on Mars. In addition, silica deposits are also favorable to the preservation of microbial fossils. So this is therefore not only a place that was likely favorable to life, but also a place where we have good chances to find remains of organisms. So following Opportunity and Spirit, the Curiosity rover landed in 2012 in Gale Crater. What makes this area particularly interesting is the central mound inside the crater, which is called Mount Sharp. This crater was interpreted as being the location of a dried up lake. Over time, layers of sediments carried into the lake by fluvial networks settled down at the bottom of the lake. And when the lake dried up, the sedimentary layers were eroded, and this mound is all what is left of them. This is a view of Mount Sharp taken by the Curiosity rover from the ground. And so the age of this mound has been estimated to 3.8 billion years, so older at the bottom, to 2.8 billion years at the top. Before the Curiosity rover landed, instruments in orbit analyzed the composition of the rocks inside the crater. This is a mineral map which shows that the older lower layers, which are located here, contain clay, which forms in warm, wet, and pH-neutral environment more favorable for life. Meanwhile, the upper layer, more recent, contains sulfates, which form in a colder and more acidic environment, and an environment less favorable to life. Therefore, what the layers of this mound represents is a record of the geological history of a crater and a record of the effect of climate change on Mars between 2.8 billion years ago and between 3.8 billion years ago and 2.8 billion years ago. Now, when the Curiosity rover explored the crater, it confirmed those interpretations that were made from orbit and also made several new discoveries. So during its exploration, the Curiosity rover passed through fluvial into a lacustrine environment. The fluvial environment is characterized by these ancient stream beds. Here, this sedimentary conglomerate consists of large round pebbles that are very similar to those that are found on stream beds on Earth, such as this one. We can tell the fluvial origin of these pebbles because of their characteristic round shape and their size, which are caused by the transport and abrasion by a sustained water flow. We can also infer the flow direction of the water by looking at the layering of sediments such as those. The layering at various different angles, called cross-bedding, is caused by the passage of waves of sand on top of the other inside a current. And we can tell from the angle of these layers that the direction of the current here was from the southeast. So this suggests, if we look at different rocks like this on the ground, this suggests that the layers were formed by sediment moving down the delta and deeper into the lake. Further inside the crater, Curiosity drilled holes to analyze the material under the surface. What it found was a clay-rich, fine-grained mudstones with low salt concentration. Like clays that were discovered at Overside, the formation of these clays require a standing water with a neutral pH and water that is stable over a relatively long period of time. So we can tell from Curiosity's analysis so far that about 3.7 billion years ago, Gale Crater was likely a wet environment consisting of fluvial channels flowing into a crater lake and depositing layers of sediments in the process. this environment could have sustained life, and evidence of this life may be preserved in the sediments. Some of the most important compounds that were discovered by curiosity in the Gale crater sediments are complex ancient organic molecules. Organics are carbon-containing molecules that form a building block of all life on Earth. At the surface of Mars, radiations and the salt compound perchlorate destroy the organics at the surface. So to find organics, Curiosity utilized a drilling tool, which is installed at the end of this arm, pictured here, in order to probe the interior of rocks. And those images show different sampling sites, and this particular site, Cumberland, is the one that showed the highest concentration in organics. This discovery is a major milestone in the search for life, but it isn't a proof of life by itself, because although organic molecules are created by biological process, they can also be created by geological processes. Curiosity also detected the presence of another major organic molecule, this time in the atmosphere. This organic molecule is methane. More precisely, it detected seasonal variations of methane in the atmosphere, as illustrated on this graph, where we can see that the concentration of methane start increasing at the beginning of a Martian summer, and start decreasing at the beginning of the fall, with the lowest points in the winter and in the spring. This seasonal cycle is of particular interest because it implies an active ongoing process. So the sunlight and chemical variation break up the methane molecules in the atmosphere within a few centuries. Therefore, any methane that is detected today must have been released recently. And methane on Earth is mostly created by microorganisms. So finding variations of methane in the atmosphere does have implications for life on Mars. However, methane can also, in some conditions, be produced by non-biological processes, such as reaction between water and rocks. So while this is another major finding, this isn't in itself evidence of life. And we will likely need to wait for future missions and new tools to identify the type of methane and be able to say whether it is biological or geological in origin. To summarize, the discovery of organics completes the list of necessary ingredients for past or present life on Mars, which includes water, nutrients, an energy source, and organic compounds. And while these discoveries are not evidence of life, they do present compelling evidence that Martian life could have existed in the past, and that there is ongoing activity today that could potentially be related to liquid water or to life. Now, if there is life on Mars today, where would it be? It is very unlikely at the surface, because liquid water is unstable at the surface and no lakes, no river can exist there. Also, the radiations at the surface are very damaging to living organisms. So what about underground? We know from data from the Martian orbiters that there is water underground, large reservoir of water ice in the subsurface. This map here, everything that's in color represents ice in the subsurface that's located within about 3 feet from the surface. And we also observe ice inside impact craters in the high latitude, generally above about here and here in the purplish area. And this ice is likely ice that was located in the subsurface and that has been excavated during the impact and that has been relocated inside the crater. So we know there is plenty of water ice in the subsurface of Mars. Now, what about liquid water? Well, in 2018, the ground-penetrating radar MARSIS on the ESA's Mars Express orbiter detected a large saltwater lake under the ice at the south pole of Mars, about 0.9 miles beneath Mars' surface. And this year, new radar observations by the same instrument confirmed the discovery and found also 3 smaller lakes surrounding the large one. This is the South Polar Cap, and this is the area that was scanned by the radar. On this image, the small blue dots represent the strongest radar reflections, which have been interpreted as liquid water. The way the MARSIS radar works is by recording the radar signal that is reflected by the various subsurface material. Different material reflect the signal in different ways, and the reflection from liquid water is stronger than the reflection from other materials such as rocks and ice. So by analyzing the various signals, we can discriminate between the different types of material and detect the presence of liquid water. So this discovery is especially significant because it is the very first body of liquid water that has ever been detected on Mars. The largest lake is estimated to be 18 miles across and is surrounded by 3 smaller lakes, each a few miles wide. And all of those lakes probably have a pretty high salt content in order to remain liquid at the low temperatures. So, those lakes are environments with liquid water, they are sheltered from radiation, and they are environments where nutrients can be produced out of the minerals. Therefore, they will likely have all the ingredients needed to sustain life. On Earth, some subglacial Antarctic lakes, such as Lake Vostok, are home to single-cell organisms that not only can survive in very salty water, but they also use the salt as part of their metabolism. So we can imagine that similar ecosystem may exist today in the underground Martian lakes. So we have made major discoveries in the past 15 years in our search for life on Mars. Where do we go from here? Well, in the immediate future, 3 missions will help us gather more data and hopefully answer more of our questions. The NASA Mars 2020 mission, which includes the Perseverance rover, which launched this year. There's also the China's Tianwen-1 mission, which also launched in 2020. And launching in 2022, there will be the European rover Rosalind Franklin. So I am here going to give a brief overview of the mission of the Perseverance rover. So the Spirit and Opportunity rover confirmed that liquid water once existed at the surface of Mars. Building on that discovery, Curiosity found that the conditions on Mars over 3.7 billion years ago were favorable to life as we know it. Now, the NASA Perseverance rover, which will land in February 2021, will directly search for signs of past life on Mars, and it will also collect soils and rock samples that will be returned to Earth by 2031. And getting those samples back to Earth will be the most ambitious Mars mission in history. This is the landing site of the Perseverance rover in Jezero crater. The main interest of this site is this landform, which is interpreted as a delta. Delta are fan-shaped accumulation of sediment which form when flowing water encounters standing water, such as a lake, and drops its load of sediment. So the interpretation of this landform is that over 3.5 billion years ago, river flown over the Jezero crater wall and created a lake, and this is an artist's representation of what this area may have looked like at the time where the lake existed. and the Perseverance rover is going to land somewhere within this ellipse. So the orbiter spectral data shows that sediments that are containing clays and carbonates within this delta. As I've mentioned before on several sites, the clay form in water with a neutral pH, which is indicative of an habitable environment. And therefore, microbial life could have lived in G0 at the time where there was standing water in the crater. And if so, the remains of his organism might be found in the delta X sediments, as clay are particularly conducive to fossil formation and preservation. How will Perseverance search for life? So Perseverance will be carrying numerous instruments, and I'm not going to go into the details, but we have here, for example, a Raman UV spectrometer called Sherlock, which will produce a detailed map of the minerals present, including any organics. The spectrometer even has a psychic camera called Watson to help it in its task. We have here another instrument called Pixel, which will study the detailed chemical composition of the same area. Then here, for example, we have another instrument called RIMFAX, which is a ground-penetrating radar, which will study the structure of the subsurface at the site and could potentially detect pockets of water up to 10 meters deep. So overall, many of these instruments will look at the structure and chemistry of the material in unprecedented detail and search for biologically important elements, mineral molecules, including organics, and structures that are characteristic of living organisms. However, even if some instruments on Perseverance sees or find something that looks like an ancient microbe, we likely won't be sure that we have found life on Mars until we are able to bring the samples back to Earth. Indeed, despite our technological advances, some of the necessary laboratory analysis can be performed remotely, at least not with the degree of precision that would be required to support a claim as groundbreaking as the discovery of life on Mars. On a side note, Perseverance will also have some company at the surface. There will be an helicopter drone, picture here in the background, called Ingenuity. It will be deployed and explore the rover surrounding, and not to find life, but in order to learn about the feasibility of flying vehicles on other worlds. This will be the very first helicopter which will be attempting to fly on another planet, and if it's successful, it could lead the way to more missions featuring flying small aircraft. To summarize, the environmental conditions on Mars over 3.7 billion years ago were favorable to the existence of life. We don't have evidence yet that life existed, but with each new mission to Mars, we are progressively getting closer to having an answer. Currently, the conditions at the surface of Mars are hostile to life. However, the detection of underground lakes and the seasonal variation of methane in the atmosphere suggest that possibly life could be present today beneath the surface, maybe in underground lakes or in hydrothermal systems. And in the words of NASA's Associate Administrator Thomas Zurbuchen, with these new findings, Mars is telling us to stay the course and keep searching for evidence of life. Thank you for listening.